Hello friends, in previous lecture we discussed with the basic gates and binary bits and some derived gates. So in derived gates we are aware with the 4 gates, that is NAND gate, NOR gate, XOR gate and XNOR gate. So out of which 2 gates, NAND gate and NOR gate, these are known as universal gates, because using NAND gate we can obtain the truth table of AND gate, OR gate and NOT gate. Similarly, using NOR gate, we can obtain the truth table of AND gate, OR gate and NOR gate. So, because of NAND gate and NOR gate, we can easily obtain the truth table of AND gate, OR gate and NOT gate. That's why these gates are known as universal gates. So, we will see how to use NAND gate as universal gate so that we can obtain the truth table or the equation of basic and basic OR and basic NOT gate. So let us see first of all a realization of basic AND gate, basic OR gate and basic NOT gate using NAND gate. So here first, suppose we are having one input A, and if I apply then one input A to NAND gate, 2 input NAND gate, if I am applying same value of A variable, then the output of this NAND gate is Y equal to A and A whole complement. And we know the logical theorem A not A, it is always equal to A. So if A not A operation is there, then I can write only A by using this logical theorem. Instead of A and A, I can write A and the complement is as it is. So if I am applying A as an input to NAND gate, I am getting its complement as output. So this is the realization of basic logic NOT gate using NAND gate. That is one thing. Second, realization of AND gate using NAND gate. Suppose I am having 2 inputs A and B. If I apply those 2 inputs to NAND gate, this is NAND gate, then I will get output A and B whole complement. That is the NAND gate output for 2 input variables. If I apply same input in next level NAND gate, let me take one more NAND gate here. Now here, this is NAND gate number 1, this is NAND gate number 2. For second NAND gate, I am applying the output of NAND gate 1. So A and B whole complement and A and B whole complement. So what is output of second NAND gate? It is A and B whole complement dot, that is AND operation, A and B whole complement, whole complement. This is the NAND gate number 2 output. Let me take that equation here as it is to simplify it. A and B whole complement and A and B whole complement, again whole complement of both the terms. Now we are aware with the De Morgan's law theorem. What De Morgan's law theorem tells us, if there is A dot B dot A dot B whole complement, then we can write this equation in, suppose this is first term, this is second term, we are having AND operation between them, and for entire term we are having complement, then we can take A dot B complement, that is complement of first term, and instead of AND operation we can take OR, and the second term as it is with its complement. That is De Morgan's law theorem. So if I apply that theorem here in this case, what is the simplified form? A dot B, that is first term I am taking here. For this is my first term. So according to this De Morgan's law, let me take the complement of first term once again. The original term was A and B complement, and according to De Morgan's law theorem, again it's complement. So there is a double complement of the same term, and instead of and we are taking or. Similarly for second term, original second term is A and B complement, and according to De Morgan's law, it's double complement. So again here we will apply one logical theorem. What it tells, if A double bar is equal to A, so both the terms are equal. If we are having double complement of any variable, its equivalent term is its uncomplement form. Okay, means A double bar is equal to only A. So if I apply that rule here, then I can write here A and B plus, similarly here there is a double complement of A and B, so I can write A and B. So this is the next level of expression. Again we will use one theorem here. Suppose we are having a similar term in a or operation, then its equivalent is always same term only for once. So if I use that rule here, then I can write it is a and B, because the same term is getting repeated. So you can write it only for once. That is the logical theorem. So it is final conclusion is y equal to A and B. So if we are applying A and B as input, what we are getting at the end? Their AND operation. Means what we did here, using NAND gate, we have realized the AND operation. Next, realization of basic OR gate using NAND gate. Again, let me take two variables A, B. I am applying same input to the first AND gate. This is the NAND gate number. So A and A. Similarly, I am applying here input for second NAND gate, B, B. So what I get here, output of first NAND gate is A and B whole complement, and similarly here output of second NAND gate is B and B whole complement. If I apply them as an input to the third NAND gate, this is NAND gate number 3. So what I get here, y is equal to first term, that is A and A whole complement dot, that is AND operation, second term is B and B whole complement, and because of NAND, whole complement of the entire term. Let me take that term here as it is. Why? We have to explore it, that's why I am taking it. A and A whole complement and B and B whole complement and entire term complement. Now again here you can apply the De Morgan's law theorem. So what it tells, De Morgan's law theorem, if we are having two terms A and B whole complement, then what De Morgan's law theorem tells us, it is always A complement plus B complement. So if I use that theorem here, consider this as A and this as B. Okay, this is first term, this is second term, and if I use this De Morgan's law, I can write it here. First term A and A whole complement, again it's complement. and instead of AND we are taking OR operation. Second term as it is. Second term is B and B complement and its complement according to De Morgan's law. Now again we are aware with the logical theorem. If there is A and A, we can take only A for once. That is the logical theorem. So if I apply that theorem for both the terms, then I can write, instead of A and A, I can write only A and its complement. This is first complement and this is De Morgan's law second complement. Plus, similarly, B is repeated here, so write it only for once, its complement, and this is De Morgan's law double complement. Again we are aware with the rule, if any variable is having double complement, write only A. The result is its equivalent uncomplement term. So if I apply that rule here, so A double complement means A plus B double complement means B, and finally we are getting Y equal to A or B. So what is this? We are having two inputs AB for NAND gate, and at the end we are getting output as OR gate. So this is the realization of basic OR gate using NAND gate. So what we did here, using NAND gate, we have realized basic NOT gate, basic AND gate and basic OR gate. So because of this NAND gate is known as universal gate. In next lecture, we will discuss how to realize these three basic NOT gate, NAND gate and OR gate using NOR gate. Hello friends, now we are going to start with the realization of basic AND gate, basic OR gate and basic NOT gate using second universal gate, that is NOR gate. So first of all, we will see realization of basic gates using NOR gate. First, if I apply single variable input, that is A, as an input to NOR gate symbol is like this, OR gate with bubble. So if A is a input, so that input I am applying for two input NOR gate. So we are aware with the output of NOR gate, that is A or B, sorry, we are applying same here. So A or A whole complement. Okay, so let me take that equation here as it is, A or A whole complement. We are aware with the logical theorem, A or A equal to A. So if I apply that theorem here, instead of A or A, let me write that A only for once using that theorem. So what is final? Y equal to A complement. So if NOR gate is having input as A, what is output? Its complement. So this is the realization of basic NOT gate using NOR gate. Now second, realization of basic OR gate using NOR gate. So let me take two variables A and B. Take NOR gate. So we will be having output here A or B whole complement. Split that output similarly for second NOR gate. This is NOR gate number 1, this is NOR gate number 2. So we are applying the same input for two input NOR gates. These are the inputs for second NOR gate. So here we will get the output in this form, A or B whole complement, that is first term, plus A or B complement and the complement of entire term. So let me take that term here as it is to explore, A or B complement plus A or B complement and whole complement. So if I apply the De Morgan's law theorem, what De Morgan's law theorem tells us, if we are having two variables and their whole complement, then De Morgan's law theorem tells us it is always equal to complement of first term and complement of second term. So if I apply that logic, De Morgan's law theorem here, and if I consider this as first term and this as second term, so I can write it using De Morgan's law theorem, the first term complement instead of or and operation, and the second term complement. This is using De Morgan's law theorem. Again, we are having one logical theorem. What it tells, if we are having double complement of any term, it is always equal to its uncomplement variable. Okay, so if I apply that theorem here, it's not that is only the underline. Okay, so this is a double complement of first and this is a double complement of second. So what we can write here using that, A or B and A or B. Again we are having one logical theorem, if A and A, it is always equal to A. Use that theorem here. So using that I can write this is as a final output. So this is what realization of NOR gate using, realization of OR gate using NOR gate. Okay. Now the last one is realization of basic AND gate using NOR gate. Again we require two inputs A, B. Now apply same input to first NOR gate and apply second input for twice to NOR gate number 2. This is first NOR gate, this is second NOR gate. So for first NOR gate I am applying A for twice and for second I am applying B for twice. What we will get, output of first NOR gate is A or A complement, B or B complement. So if I apply those two outputs as an input to next NOR gate, so its output is Y. Let me write that output here. Y equal to first term A or A complement, that is the first term, plus second term B or B complement whole complement because of this NOR operation. Now we have to explore this. So according to De Morgan's law theorem, what it tells, if we are having A or B whole complement, De Morgan's law theorem tells us complement of first term and complement of second term. So here if I apply that theorem here, so if I treat this as a first term and this as a second term, I can write first term, this is my first term, I will take its complement, and instead of and we are taking, instead of or we are taking and here, and this is my second term. Okay, and its complement. So now we are having complement, double complement of first, double complement of second. And what is logical theorem? If any variable is having double complement, then it is equal to its uncomplement. So if I apply that rule here, I can write A or A and B or B. Again we are having one more theorem, A or A is equal to always A. Apply that theorem here. So for this term I can write A, this dot as it is, and the second B. So what is final? Y equal to A and B. So this was the realization of AND gate using NOR gate. So in this way what we did, we have just realized the basic NOT gate, OR gate and AND gate using NOR gate. That's why these NAND and NOR gates are known as universal gate.